Hi, welcome back. So I left you with the idea of looking at the pros and cons of ground-based and space-based telescopes. So if we just come back to this figure for a moment. So I'm sure you probably discussed many things, but an obvious one, of course, looking at this is that an advantage for certain wavelengths is that you literally have to be in space, or you simply cannot do that waveband. So for some wavebands, as we said already, you literally have to be in space. For other wavebands, then there are, for instance, like in the optical or in the near infrared, you have a choice. You could do it from the ground or from in space. So other things to discuss might be, for instance, the cost. It is really expensive to launch anything into space, and the bigger it is, the more expensive it is to launch it. So launching satellites into space usually costs you a huge amount of money before you even start to worry about what the instrumentation and everything and your telescope. So cost is definitely a big advantage of putting your telescope on the ground. Other advantages of working on the ground, of course, is that you have access to your telescope, and particularly the instrumentation. So if anything breaks, you can repair it. But more usually is that especially the detector technology improves over time, you can replace the detectors on the same telescope and improve your telescope enormously, its sensitivity. So that's a big advantage of being on the ground. You can continually develop and upgrade your telescope. In space, that's usually not the case. The exception was the Hubble Space Telescope, which was in low enough orbit that it could be refurbished and was successfully many times. So that's another issue. Again, thinking about the optical in particular and the infrared, then even though you can do it on the ground, you still have to contend with the effects of the Earth's atmosphere, like a sort of twinkling and blurring effect of the Earth's atmosphere, which are a problem, even in the optical. And so there are quite a few very successful satellites working in the optical and the near infrared that do operate in space, even though you can do them from the ground, because you need to get away from the residual effects of the Earth's atmosphere. So hopefully you brought out some of those points. Okay, let's keep moving. So now let's get to the core of what I want to talk about in this lecture, which is what is the primary role of radio astronomy in all of this multi-wavelength astronomy that we talked about at the beginning. I mean, as you will hopefully see over the course of the next couple of weeks, then radio astronomy actually impinges on nearly every aspect of astrophysics. But I would say, and this is probably a personal viewpoint, is that the primary role of radio astronomy is to probe the interstellar gas in its various forms. The one thing you don't really use radio astronomy for is to just look at normal stars. Okay, I mean, basically you can't even really see them at radio wavelengths. So it's the stuff between the stars that really comes into its own when we're probing them at radio wavelengths. And I'm going to break this down into the sort of three main forms of interstellar gas, so by its various phases, so ionized, atomic, and molecular, in that order. And I think, again, from a personal viewpoint, because it's the kind of thing I do, but I think it's also borne out by the kind of things that the vast majority of radio observatories are usually studying. Often they are looking in some way or another at ionized gas in the interstellar medium, the intergalactic medium, or circumstellar around near stars, but not the stars themselves. And so let's start to look at break this down into some of the sort of basic physical concepts. So how does gas get ionized in the first place? So two ways of doing that. You can either have you can do it with radiation, with photons, basically, can ionize a gas. So usually you will then need a source of extreme ultraviolet radiation reasonably nearby to the gas that we're talking about. So basically you need a hot source, often a hot star, that is photoionizing the gas that is surrounding it. Okay, and we'll look at some examples in a moment. The other main way of ionizing gas is to, so rather than exciting the electrons out of their bound levels, you can smash them out of their bound levels by collisions. So putting energy into atoms through fast-moving collisions. So normally this involves a kind of shock wave where you have very fast-moving gas hitting slower-moving gas, which results in a shock and often then results in ionized gas in its wake. So again, let's expand on those with some examples. So some examples of photoionized nebulae first. So a nebula is this general word for like an extended source of emission on the sky, as opposed to sort of a point source like a star. So there are many forms of nebulae out there in astrophysics, but just to highlight a couple that are photoionized and therefore good radio sources. The first of which are called H2 regions. So H2 is one of the ways in which ionized hydrogen is designated. So the 2 here is the spectroscopic notation, which means singly ionized hydrogen, but in spectroscopic notation, it is referred to as H2, and hence a region of ionized hydrogen in this circumstance is referred to as an H2 region. But it does particularly pertain to regions of gas that have been heated up by a very massive hot young star that has recently been born, and so that it is heating up the gas around it that it literally just formed out of the cloud of initially molecular gas. But when you put a hot star in the middle of that, the ultraviolet radiation will heat up and ionize all the surrounding hydrogen gas. And you've got an example here, beautiful image of the so-called Orion Nebula, which is the colors here are just false, representing intensity of radio continuum emission from that nebula. So you've got hot stars in the middle that you can't see at all in this image. All you're seeing is this big bubble of hot gas. And this is at the beginning of a star's life. Very similarly, you also have an example of photoionized nebulae at the end of a star's life. So a star like the sun, at the end of its life, it will eject the outer envelope of the star entirely and leave behind a very hot, initially a very hot core, the sort of stellar remnant as it's referred to. And so again, we have this situation where you have a shell of gas that's now expanding away from the star, and it's heated up and ionized by the core of the remnant star left behind, which is very hot. And this example here actually comes from a survey that I was leading, and these data were reduced and produced by Tonya Irabor, who's my PhD student originally from Nigeria, who has been working on this survey called the Cornish Survey. And kind of quite different, but in a sense the same physics. You can't get much hotter, of course, than the original hot Big Bang that we believe started off the entire universe, when the whole universe was just one big ball of hot gas that was expanding and cooling down, and illustrated in this schematic here. And so when the gas got cool enough, basically it became transparent, and at that point we can actually get this strange idea of looking back all around us in all directions because of the finite speed of light. The further you look back in distance, you're also looking back in time. So in principle, you look in any direction, you should be able to see the afterglow of the Big Bang itself. And this was one of the key discoveries of radio astronomy, was this discovery of the so-called cosmic microwave background. So this is a picture of not the emission itself, which would just be extremely boring and uniformly flat because it's basically the best black body that nature has ever produced. But these are the fluctuations, which are only like, just a few parts in a million of this very uniformly smooth background emission that we see everywhere around us. So this is basically the whole sky, and there's these tiny fluctuations, which are, intriguingly the kind of the imprint here of some of the physics that's going on as part of the early universe. And so still, a key part of radio astronomy today. And the SK will be certainly looking at not necessarily the microwave background itself, but sometime later trying to find out when these irregularities condense into the first sort of concentrations of hydrogen gas and the first stars and galaxies. But all of these processes that are heated up by radiation tend to emit by one of the two main processes in radio astronomy, which is the so-called thermal free emission, or Bremsstrahlung as well is another the sort of German word that's associated with the same process. So free means you've got a free electron. It will pass by a positively charged nucleus, an ion, and it will get accelerated. And as you know, any accelerated charge will emit. And so this emits a continuous distribution of different frequencies. So this is a continuum process. And because the electrons are moving around just thermally with velocities associated with their temperature of the gas, then this is a thermal process. Okay. So the other type of ionization is collisional ionization. Okay. And one classic example of that is another process at the end of a star's life, but this time much more energetic, the so-called supernova explosions, extremely energetic events, when you get the whole outer layer of a star is just ejected violently into space at mildly relativistic speeds, so significant fractions or percentages of the speed of light. And so then that gives you the very high speed shock that you need to collisionally ionize the gas. And you can get supernovae supernova explosions from two different types of star. You can get the single massive star that's just run out of fuel and is ending its life, and that will explode as a supernova. Or you can, in an interacting binary system, you could have a white dwarf that is accreting mass from a companion, and if it gets to its limiting mass, the Chandrasekhar limit of 1.4 solar masses, and is tipped over the other side, then it will also explode as a supernova. And just to show you, again, a nice little movie of radio emission from a supernova. This is in another galaxy, so this is extremely high resolution radio astronomy, which again will be a feature of this course. But for now, let's just have a look at what's happening here. So you can see that there's roughly a kind of shell. It's not perfectly symmetric. That's expanding over time. So this is a sequence, like a movie, of this explosion happening, over the period of a few years. You can see this shell of gas expanding. But again, this is all radio emission here from this collisionally ionized gas. So other ways in which you can get collisions, you can get them from various types of jets. So we see this again and again in astrophysics. You will have some kind of accreting disk of material, accreting material onto a star, and then perpendicular to that, you will get a fast-moving jet. So a couple of examples here. You've got, this is a picture of a jet, stubby-looking one, really, from a new star. Okay, so these are stars in the process of forming. So the accretion is happening onto the protostar, and the jets are perpendicular to the disk. And so you get radio emission here. So the contours are the intensity of the radio emission. Very similar situation, again, towards the end of stars' lives, again in these binary systems, where you might this time, again, have accretion onto a companion. If those companions are neutron stars or even black holes, then you can get very energetic relativistic jets arising from these. So again, particles streaming out at close to the speed of light. Here you can see a time sequence of radio images of one of these types of sources, and this is giving rise to this moving material moving outwards extremely high speeds. Okay. Again, I'll just point out that these observations here were taken by the DARA PhD student Willis Abonyo from Kenya. And another DARA student here, Emmanuel Bempong Manful from Ghana, looking again at relativistic jets, but this time on a vastly different scale, because at the center of these jets is a supermassive black hole at the center of a galaxy that is being fed gas because it's an active galaxy, and that gives rise to these jet phenomena, but now extending way out of an entire galaxy into intergalactic space, giving rise to these lobes. So again, beautiful radio jets here in these radio images. So what is the type of radiation mechanism that is giving rise to those collisionally ionized sources? Again, this is a kind of a rule of thumb. It's not, there will be exceptions to this, but usually those kind of sources that have very fast moving expansion of gas and shocks and jets and those kind of things will be emitting via a non-thermal process, the so-called synchrotron process. So this involves very fast moving particles, relativistic electrons basically, and strong magnetic fields. You need both of those ingredients. And so the electrons are this time spiraling around the magnetic field lines. You've got relativistic electrons, so these are not moving at their normal thermal speeds. They've been accelerated by the shock processes in these sources up to relativistic speeds, and are then spiraling around the magnetic field lines. Again, because they're accelerated, they're emitting, and so you get this synchrotron process radiation. So this is a non-thermal process. Okay. So just to finish up here, I'm just going to give you a little numerical exercise. So have a calculator ready. You will have noticed in those previous pictures some colors for here, for instance, and here, for instance. So these colors are to do with the what we would call the spectral index, which is actually the slope of the radio continuum spectrum. Okay, so basically, how is the radio flux changing with frequency for these types of sources? So, like in a lot of science and astrophysics in particular, we can express that as a power law. So here, S nu is the symbol we normally give to the flux of a radio source as a function of frequency. Okay, so this would, in SI units, would be in watts per meter squared per hertz. But as you'll see, we normally in radio astronomy use another unit called the Jansky, which you will come across later. And here it's in millijanskys. And how that varies with frequency can be expressed as a power law. So nu to some power alpha, and this alpha is what we would refer to as the spectral index. So you'll be doing a lot more of this in various times, I think, throughout the training. But for now, just treat this as a mathematical little puzzle. So if we can express it as a power law, I'm giving you a particular source that has a flux of 0.65 millijanskys at 1.5 gigahertz and 0.26 millijanskys at 5.8 gigahertz. So I'm giving you the flux at two different frequencies. Can you come back and tell me what the spectral index, what the value of alpha is in that case? Okay, I'll leave that with you and we'll come back after the break. So again, just take 5 minutes or so.